Hello everyone, welcome to Microsoft Application Migration session, part of AWS Innovate online conference. My name is Srivan Tattanayake and I'm a partner solution architect here at Amazon Web Services focusing on Microsoft technologies. In this session, we are going to explore a few options available for you to easily migrate Microsoft applications to AWS. There are multiple ways you can move your existing workloads to AWS. Each has its own use cases, advantages and disadvantages. For the best interest of time, we will dig a bit deep more into only some of these services and explore how they work. We will explore simple ways to migrate your workloads like VM import and export, and then look into some modern way to move your workloads using containers. For many of you, containerization of your workload may be quite new. We will dig a bit deep into containerization and share a short demonstration how you can containerize an EXE application easily. You will learn about Amazon Elastic Container Services and its use cases related to Microsoft applications. We hope that by the end of our time together, you have developed an appreciation of the AWS services that help you to migrate Microsoft apps onto AWS. So let's get started. Imagine you have legacy Microsoft applications running on Windows 2003. AWS is the only cloud service provider that still supports 32-bit operating system and allows you to spin up virtual machines running 32-bit operating systems such as Windows 2003. A lot of organizations are in a situation where upgrading existing OS is not an option. It could be due to a number of reasons such as outdated documentations, lack of organization knowledge about application, or application vendor does not support the new operating system, discontinue the product, or the company no longer exists. In any of these cases, lift and shift may be the only option. AWS provides a few services to easily do lift and shift migration. If you have Windows applications with some acceptable downtimes, what are some simple options to migrate that workload to AWS Cloud? For those workloads where some downtime is possible, VM import and export is a simple yet powerful way to migrate your Microsoft workloads to AWS Cloud. Consider a case where you are running a virtualized environment on your on-premise data center. If you want to move one of your virtual machines to the cloud using VM import-export, you first stop the virtual machine. You then export it into one of the supported formats like OVA, VHD, VHDX, VMDK, or RAW. After exporting the image, you kickstart a command line and punch in some commands to import that image into S3 bucket. If the image is big, it can take some time to upload using a slow internet connection, but you can monitor the progress with another command. Some large customers use AWS Direct Connect for faster connection between on-premise environment and AWS Cloud. Regardless of how you connect, your data at transit will always be encrypted. Once the upload is completed, AWS will kickstart an image conversion process which will produce an Amazon machine image out of which you can spin up EC2 instances. If you want to spin up VM in another region, you can simply copy the Amazon machine image into the new region and use it. Images imported to AWS can be exported back. This will prevent you from lock-in. Please note that only the images you have imported to AWS can be exported. For example, you cannot export an Amazon provided pay-as-you-go license included image to your local environment for obvious license compliance reasons. VM import and export is suitable for simple migration scenarios. If you want to live replicate or run in VMs into AWS, AWS Server Migration Service or our partner solutions like Cloud Endure is a great place to start with. To understand how AWS Server Migration Service work, imagine you have a virtualized environment. First, you download an image that contains AWS Server Migration Connector. You can download a connector that supports either a VMware or Hyper-V. You import this image to your virtualized environment, then start the connector like any other virtual machine. With a few configurations, you can then connect your virtualized environment into AWS Cloud. The connection can be through internet, direct connect, VPN, or the data transfer is always encrypted. The cool thing is you don't need to install any agents in your VMs. Once replication completes, it will create a new Amazon machine image which you can use to spin up new EC2 instances. The server migration connector exposes a local website with a nice user interface you can use to check the connection and replication status. This is how it looks like when the server migration connector establishes the connection to AWS Cloud. Once the connection is established, your on-premise servers will appear on AWS console. You can then select which servers you want to replicate, kickstart a replication job that will replicate the block level content. Once the replication job completes, you can start a new EC2 instance out of the image the replication job has created. Being the first cloud service provider, AWS has a great and matured partner network. Our partner network has built a strong ecosystem of tools and services for our customers. There are many AWS partner solutions that will make your life easy during migration. For example, during initial stages, TCO Logic can assist in building your business case for cloud migration. It can collect data from your existing virtualization environment logs, Excel sheets, and estimate the cost of current infrastructure and compare it against AWS equivalent. The tool can collect data like CPU memory utilization from on-premise servers and provide instance size recommendation. It is smart enough to consider your current Microsoft license portfolio and recommend different licensing options that can save money. Cloud Endure is also a powerful partner solution that can live migrate virtual machines to AWS. Feel free to explore our partner solution that can assist you on your cloud migration journey. If you are not planning to do lift and shift migration and OS replication modernization still is in your agenda, containerization is a great way to move your workload to cloud. There are a lot of reasons why you should consider containers as a first-class citizen in your cloud migration journey. For example, containers are super easy to create. They are portable across many cloud service providers. More importantly, Microsoft has taken containers as a first-class citizens on Windows platform. Windows 2016 servers has now native Docker support. For those who are not familiar with Docker containers, let me give you a 2-minute crash course. Let's compare traditional virtual machines to containers. Traditional virtualization based on technologies like Hyper-V or VMware abstract the host hardware, whereas containers abstract the host operating system. Both need some physical servers to run. Both need some host operating system. In the case of virtual machines, you run something called a hypervisor that abstracts the hardware to the guest operating system. You then spin up virtual machines on top of hypervisor. In VMs, shareable resources are not shared that leads to resource waste. For example, consider the two virtual machines based out of the same operating system. 90% of the OS content in these two virtual machines are going to be the same. If your OS image is 20 GB, for the two virtual machines, you will use 40 GB of storage. Think about .NET Framework. Why you need to install them on both virtual machines? Think about the complexity that comes when you try to patch. You need to patch each virtual machines. Some of the common processors OS runs are helper tasks that has nothing to do with the apps. They take valuable resources like CPU and memory that can be used for your apps. You have wasted resources which applications can use. Overall, you end up running a fewer number of apps on a given hardware. In the case of containers, multiple containers can share the same base operating system image. For example, containers 1 to 4 running .NET apps can be used a single OS image with the .NET Framework installed. Containers 5 to 6 running a Java application can share an operating system image with Java Framework installed. Overall, you can now run 6 apps instead of 2 apps on a given hardware. You have effectively increased the packing density of apps. Container images are based on a concept called layers. For example, you may start out with a base operating system image in layer 1. You then install some security updates in layer 2. You then install some application 1 specific content like .NET Framework on layer 3. And finally, the application on layer 4. Application 2, on the other hand, depends on your patch layer 2. Install its specific framework like Java Framework on layer 5 and itself on layer 6. This concept of shared layers make the containers very lightweight and patching becomes super easy. When you create images and push them into container registry, only delta changes in layers are pushed. This saves a lot of time when uploading images. If you plan to create a CI/CD pipeline with continuous push of images to a repository, you don't need to worry about uploading large images because only delta changes are uploaded. Designed correctly, patching and maintenance is easy with containers. In this example, we have two applications that depends on ASP.NET latest image. When the framework is updated, you can easily upgrade only that layer. If a new Windows update comes, you can upgrade only that layer and your application will still run. Let's now go for a demo and see how we can package a simple exe application as a container. You can also containerize applications like ASP.NET web apps that runs on web servers such as IIS, Apache, batch application as console apps, PowerShell scripts, SSIS jobs, or services such as SQL Server, to name a few. You can pretty much containerize any application that runs on Windows Server Core image. I have a sample exe application that I want to containerize. It's called my batch app. So let's run it and then see how it works. So all what it does is spin up multiple threads and then print some random numbers. If you go to the CPU utilization, you can find that it pretty much uses all the CPU available of the machine. A classic bad behaving application. So let's see how we can containerize this application. So I started PowerShell as an administrator. And I'm going to download an image from Microsoft. To do that, I'm going to call Docker pull, and I'm going to give you the name of the image, Microsoft Windows Server Core. This will go to Docker Hub and download the latest version of Windows Server Core image. So it already identified that some layers already exist, so it's not going to download the existing layers. And there's one layer that is missing. Maybe it's a new security patch or an upgrade from Microsoft. So it's downloading that missing layer. So this layer is a compressed version of the image. So the download is fast. So now it's extracting that compressed layer. So we are almost done. So the download is now complete. And if I type Docker images, you can find the latest downloaded images. So let's run a Docker container. In this case, I'm going to run it interactively. And the image that I'm going to use is Microsoft Windows Server Core. And I'm going to run PowerShell inside this container. So when I type enter, it will go inside the container because I'm running it as an interactive mode. To know the container ID, I can type host name. So you get the container ID. So if you look at the directory structure of this container, you can find that it's completely different from the container host and from many other containers running on this machine. So containers have their own file system. So the registry entries or any configuration that you modified in the container is only visible within that container. Same for the task list. If you look at the processors running inside the container, you can find that they are different from what you find on your container host. Containers start fast because they don't need to start all the processors that you need to start when you run a virtual machine. So let's make a directory inside this container. So I'm going to say mkdir and I'm going to tell it as my app. And I have started another PowerShell window in the container host. So if I type docker ps, I can find the running containers inside this container host. So I have one called 4e69. So what I'm going to do now is to copy my exe application inside my, which is inside my container host under C install my batch into the container. So I give the container ID, in this case 4e69. You can only give part of the ID as long as it distinguishes from the rest of the running containers. And inside my container, I have a folder called my app, and I'm going to copy it to that my app folder. So if you look at my app folder, you can find that exe application has been copied. So my exe is now inside the container. I can exit from the container like this because I have copied the file, or I can simply say docker stop and give the container ID from my container host. So I'm going to stop the container that I just modified. So it has the exe that I copied. The next thing I'm going to do is to call docker commit that will save these changes as an image. So the container that I want to save is 4e69. That's the container ID. You can give only part of the container ID if you like. And then I give a name for my image. So in this case, I'm going to call it my app. So from the time I do that, it will save the changes that I have made. So if I type docker images, you can find my newly created image called my app. So I can now run this container image that I just created, but instead of giving all the CPU available, I'm going to give only 20% of the CPU. So image I'm going to run is called my app. Inside that image, I have an application called my batch app. So from the time that I type enter, application will start as normal like before. But if you look at the CPU utilization, you can see that I have slice and dice my CPU and give only fraction of it. So it's now no longer using the 100% of my CPU. So far, we have containerized and ran only one application. Running a single container is easy. You can even do it manually. What happens when you start running hundreds or even thousands of containers? You need to track which containers are running, which containers are stopped, and sometimes you need to schedule containers to start on a specific time. You also need to track how much spare resources like CPU and memory are left on each hardware. All these bookkeeping tasks can be daunting in a real enterprise environment. That is why we invented Amazon Elastic Container Registry and Container Service. Elastic Container Registry is similar to Docker Hub. You can use it to keep your Docker images. However, unlike Docker Hub, it is tightly integrated with AWS Identity and Access Management, and you can easily set permissions such as who can read or write to ECR. Elastic Container Service is orchestration engine that orchestrates your containers on a cluster of EC2 instances. It knows which EC2 instance have free capacity, which one do not. If the EC2 instance running on the container fails due to some malfunction, ECS can schedule containers in a new EC2 instance. Before you start orchestrating your containers on ECS, you create something called a cluster. A cluster is an abstract overrunning set of EC2 instances. You can join existing EC2 instances, or you can spin up new EC2 instance that provides additional CPU, memory, or storage. You can also set up auto-scaling group that will automatically scale based on CPU and memory demand. Once the cluster is created, you create something called a task. A task describes what container images you want to run and constraints they need to follow. For example, you can define you want to run 2 containers as part of this task, one website, one SQL Server instance. You may then define constraints like do not run human resource website on the same EC2 instance that runs finance website due to regulatory requirements. You can also define how much memory CPU each task needs. If your task needs half of a vCPU, but the cluster does not have additional CPU capacity to provide that half a vCPU, your task will be delayed until the cluster provisions enough new CPUs or running task finishes releasing the CPU capacity it has been using. Once you create a task, you can schedule it on an EC2 cluster. However, if for some reason the task fails, let's say due to EC2 instance failure, it won't automatically start again. To maintain a desired set of tasks always running, you can create something called a service. A service defines things like how many tasks to run, what is the deployment strategy, how the task should be auto-scaled. A service can maintain a desired number of containers. If a disaster happens and some running task fails, the service will automatically start additional tasks to keep the desired count equal to the running count. ECS has built-in intelligence to know the available resources in the cluster. It can place tasks in the underlying EC2 instances in various ways. For example, bin packing placement, it first fails one EC2 instance completely with containers before moving to another instance. In the case of balance spread, ECS places tasks even in all available EC2 instances. You can place multiple tasks, hence multiple applications in a given cluster. For example, you can run human resource application as service 1 and your ERP application as service 2. If your application demands more compute resources, you can easily scale the cluster. I'm in my AWS console, so let's go into Elastic Container Service. You can find that I already have 2 clusters running. Let's go to repositories where I can keep my Docker images. So this is Amazon Elastic Container Registry. Let's create a repository. Only thing we need to give is a name. Let's call it Hello World and click next step. The repository is created and it gives you a list of commands that you can use to publish images into this repository. If you want to know the commands again, you can view push commands and you can see the commands that you saw just a while ago. So I'm in my container host where I created my image. So if I type Docker images, I can see the images in this container host. So the first thing I'm going to do is to call Docker tag. Instead of calling my app latest, I'm going to give it the full URL of my repository so that it knows that this image, when I publish it, has to go into this container repository. So you can now find a tag image with my full container repository URL. So what I'm going to do now is to first log into the container repository. For that, I copy paste one of the commands that I saw before, and I'm going to call AWS ECR get login. So now you can see the login is successful. I can now publish an image to the repository by calling Docker push and giving the full Docker image name. You can find that only the Delta changes are being pushed and some layers that already exist are not being pushed. So here I'm in my repository. So if I refresh it, you can find the newly published image or the layers appearing here. And the size is very small. So let's go to the cluster. So I already have 2 clusters created. So one cluster, for example, have two EC2 instances running. So let's create a cluster. Select Windows plus networking. Click next. Give it a name. Let's call it Hello World cluster. You can either select on-demand instance or spot instances. You can select the instance type that goes into them. Of course, you can change these parameters later. So in this case, I want to have 4 EC2 instances back in this cluster, size of the EBS volume attached to that, and the secret key. If you want to remote login into that, you can specify a remote login, the secret key you want to have, set up the network configuration, the ports that you need to open, and finally the IAM role that will be used to invoke other AWS services. Click create. So with few minutes after, your cluster will be ready because it needs to start the EC2 instance. While it is happening, we'll create some task. Click create new task. Give it a name. So this is where we are going to specify the containers that we want to run. So you can keep these things empty. As of now, the Windows support only default network mode. So what I'm going to do now is to add a container, give it a name, and I'm going to pinpoint into my repository URL. So in this case, it's going to be Hello World, and the version is going to be the latest. So when this task run, it will run this image. You can specify how much memory this needs. So in this case, I'm going to give 128 megabyte. You can do port mapping if you are running a website, but this is a batch application. I don't need to do that. And the command that I need to run. So here I can specify how much CPU you need. 1 vCPU equals to 1024. So if I want to allocate fraction of my CPU, I can specify something like 256. So the command that I want to run is my app, my batch exe. So this is what I have copied to my container image. And you can specify things like DNS settings, whether you want to mount a data volume so the containers will have the data they want. We keep everything default and click add. So I have set up my container. If you want, you can define the constraints hey, this is a char application, it has to follow these constraints. As of now, I keep the default and create a task. So my task creation is successful. My container cluster I created, hello world, is also ready. 4 instances are running. So let's run a task. So I go to task, run a new task. I specify which task I want to run. So I already have the task that I just created. I want to run 6 of them. So when I click create, it will start 6 tasks in balance spread manner. So they are as of now pending state. If you keep refreshing, some of these tasks will start. So as of now, 3 tasks has already started. If I go to task list, you can find that 3 containers are running and 3 are pending starting. If I select one of these tasks, I can go to the EC2 instance that these tasks are scheduled. So it's like a normal EC2 instance running Windows. If I want to remote login into that, I need to enable the RDP port. And I can actually remote login into these machines or the EC2 instance that runs these containers. Behind the scene, ECS just execute Docker commands on these EC2 instances to start containers. So I can connect into one of these EC2 instance, download my remote login app, and then connect into them. So it's the same Windows experience. So once I connect into one of these EC2 instances that runs the containers, I can start PowerShell. And for example, if I type hostname, you can find that's EC2 instance name. And if I type docker ps, you can find that the container, the ECS has started. If I type docker inspect and give the container name, I can find what commands the ECS executed to start this container. So you can see that it is running my app, my batch exe. You can find details about the container cluster, where it is running, some tags. Of course, if you look at this container, you can, if you want, you can even attach into that. You can say docker attach and give the container name, and you can find the application is running. It's like before, the same application that is running. So far so good. You can easily create a service like before. So create a service, give it a name. So select the cluster. So how many tasks you want to run? Let's say we want to run 4 containers for this service. If you are running a website, you can select an application load balancer. This is an exe application, so I just select none and click next. If you want to auto scale based on the load that these containers are facing or this cluster is facing, you can do that based on the CPU or memory utilization, for example. But as of now, I'm not going to auto scale, so let's skip this step. And so the number of containers I want to run is 4. So create the service. So in this case, the pending count of the task is 4, but so the desired count is 4, but the running count is only 2. So what will happen is over time, this running count will equal to the desired count. So running count is 4 and the desired count is also 4. So this is a healthy situation. Let's say something bad happens and one of these tasks dies. Maybe you restart the one. So I'm going to stop some of these tasks. I'm simulating a machine crash. So if this happens, the number of tasks now is only 4. Only running task is only 2 instead of 4. So what will happen is the service will identify that there's a deviation from desired state, and it will automatically schedule some task in another EC2 instances.
So now the desired count equals the running count.
AWS has a wide partner ecosystem to help you focus on your success and take full advantages of all the business benefit that AWS has to offer. Learn more about how our APN partners can help you and find the right APN partner for your needs. Visit AWS APN booth at our showcase. To gain more confidence and hands-on experience with AWS, watch our instructional videos and explore the self-paced lab. Attend our instructor-led classes and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Finally, validate your technical expertise with AWS and use practice exams to help you prepare for AWS certifications. You now have new arsenal at your disposal when you want to migrate your Microsoft apps to AWS. Do provide us with your feedback and let us know how we can improve the event experience for you in the future. Thank you for attending this session.